Hello everyone, my name is Ben and welcome to this video tutorial on modular arithmetic, division algorithm, and Euclidean algorithm. I'll start this video off by talking about the modular arithmetic. And that actually involves finding the remainder when we divide one number by another number. And so let's say you wanted to find let's see, color divides 7 into 3. And when you divide 7 into 3, it goes 2 times. 2 times 3 is 6. And 7 minus 6 is 1. So we get a remainder of 1. Now in modular arithmetic, we can express this as we take the dividend, which is 7, and then we say mod the divisor is 3, and this will equal what we get for the remainder, which is 1. So that's how we can express that. 7 mod 3 equals 1. So in general, you have modular arithmetic formula where you say A mod B is equal to R. And so A is going to be the dividend, and then B is going to be your divisor, and R is the remainder. And this is also equivalent to, so this means equivalent to this equation. A is equal to B times Q plus R. So A equals B times Q plus R. So we have A is the dividend, B is our divisor, Q is the quotient, and R is the remainder. And this equation is actually known as the division algorithm that we have right here. This is called the division algorithm. And so the way we could express the 7 mod 3 is equal to 1, we can actually express that just using this equation right here with the division algorithm. So we could say that 7 is equal to 3 times 2 plus 1. And so this is a true equation because we know 3 times 2 is 6, and 6 plus 1 is 7. Okay, so you're probably thinking, well, what next? Because when we talked about modular arithmetic, that helps us to get the remainder when we divide two numbers. And the division algorithm helps us express the modular arithmetic, this equation here, into this form. And so what we can do actually is repeat this division algorithm multiple times, and when we do that, we're going to get what's called a Euclidean algorithm. And what is the importance of the Euclidean algorithm is that it's going to help us find the GCD, or the greatest common divisor, of two numbers. So what we can do is start on a new board since we're running out of space here, and we'll talk about the Euclidean algorithm. So Euclidean algorithm, this is named after the mathematician Euclid. He was the father of geometry. So, like I was saying a minute earlier, we were talking about division algorithm, how we can repeat it, over and over again to help us find the GCD of two numbers, A and B. And then this is equal to D, the greatest common divisor. And so, if we start out with the division algorithm, say we have A equals B times Q, let's say just 1 plus R1, and we know that A is the dividend, B is the divisor, Q is our quotient, Q1 is the quotient, R1 is the remainder. So if we repeat this process again, we notice that B will become our dividend, and then we'll have R1 become the divisor. We'll get a new quotient Q2 plus another remainder R2. And then if we repeat this process again, we have R1 is going to equal R2 times quotient Q3 plus a new remainder R3. And then we can do it again. R2 equals R3 Q4 plus R4. And then eventually we get to a point down here we have Rn minus 2 equals Rn minus 1 Qn plus Rn. Now at some point when we continue to divide, eventually our remainder is going to become 0. So this value of Rn is going to become 0. And so what we can do actually is make this term vanish because it's 0. And then that tells us to stop with the Euclidean algorithm, that we'll actually get our greatest common divisor. And the greatest common divisor will be this value right here. This will give us the Rn minus 1. So there's our GCD. Of A and B. So if you're a little confused, with the mathematical notation, with the subscripts and everything, don't worry about that. This is just kind of how to express it in a general form. But once we put this into practice, do some examples, it will all become clear. And so let's do an example where we want to find the GCD of these two numbers, 24 and 40. So I want to find what that value is. Greatest common divisor, D. GCD of 24 and 40. And so we're going to start off with 40. And then this equals 24. And we know 24 goes into 40 one time. Plus 24 plus 16 is 40, so 16 is our remainder. And then we're going to take the 24, put it over here. And then that's going to equal 16, the remainder, times 16 goes in 24 one time, and then plus 8, that's our remainder. And then we'll bring 16 down, equals, and then we have remainder here is 8, and we know 8 goes in 16 2 times. 8 times 2 is 16, so we know there's no remainder, so we can stop. And look right here, so we have the remainder with 8, and then this is 8, so that tells us that our GCD of 24 and 40 is going to give us 8. So there we go. So that's how you would find the GCD of two numbers using the Euclidean algorithm. You just keep doing the division algorithm a repeated number of times until finally we get a 0 remainder. We can stop, and then notice that the remainder of this iteration matches up with the divisor of that iteration. So that will give you your GCD. Okay, so we're going to clear the board here, and we can try another example. So another example we could do is to see GCD of, let's see, we can do 104 and let's say 320. So we have 104 and 320. So, you know, if you need a calculator, that's okay. Unless in your class you can't use a calculator, then you'll have to do it by hand. But you can also do it by hand too. So we'll start out with 320. And we say that's going to be 104. And I believe that 104 goes into 320. Looks like probably 3 times. 3 times. And that's 312, so we have 8 left over. And then we're going to do 104 equals 8. And then does 104 go into 8? It goes 8 times 13. And then that's plus 0, so there's no remainder. So actually that one was pretty easy. We actually got the same numbers we did last time, right? Which was 8. So that's our answer. GCD of 104 and 320 is 8. Okay, so let's try another one. Let's say we have GCD of 75 and let's say 4 55. Okay, so we'll have 455 equals 75. And how many times does 75 go into 455? That's going to be 6 times. 75 times 6 is 450. So we'll have 5 left over. And then we'll have 75 is equal to 5. And I think that's times 15 plus 0. So we can see that the GCD of 75 and 455 is going to give us 5. Okay, so we probably want to do one where we can repeat this like several number of times. Let's say GCD of 48 and 62. 48 and 62. So we'll do it over here. We'll have 62 equals 48. Goes in one time. And then we have, looks like 14 left over. Then we have 48 equals 14. And 14 is in the 48 was like 3 times. 42. And then plus 6. And then we have 14 equals 6 times, let's say it was in twice, 2 times plus 2. And then we have 6 is equal to 2 times 3, and then plus 0. So we know we can stop right there with 0 remainder. And it looks like these numbers with 2 match up. So we know that our GCD of 48 and 62 is going to be 2. Okay. So another question we want to ask ourselves is, when we have the 2 numbers that we want to find the GCD of, we usually want to help us solve that equation that we talked about at the end of the last video. It was AX plus BY equals D, and D is the GCD of those 2 numbers, the greatest common divisor. And this was called the Diophantine equation. And so the question is that, does this, can we find integer solutions x and y that satisfy this equation for the 2 numbers that we have, a and b? And the answer is yes. Usually we can, as long as the numbers a and b, as long as the numbers divide, the greatest common divisor divides a and b, then that's true. So we can look at our last example here, and we'll probably need a new board to do that. And so we want to solve this equation. We'll write it down here. So 48x plus 62y equals the greatest common divisor d. So we want to find those integer solutions, x and y, that satisfy that equation. So basically, we're just trying to find the linear combination of these numbers, and when we add those together, that'll give us a value of 2, the greatest common divisor. So you can see this equation, you probably learned in algebra that this is a line, but we want to look for only just the integer solutions. We don't want to look for all real solutions, like decimal numbers, square roots, or fractions, anything like that. We're just only interested in the integer solutions. Okay, so we'll start a new board and we'll see how this works. So here's the equation we want to solve. y, yep, equals 2. And we're going to just go ahead and do our division over here that we did, just to review again that we had 62, that was 48, 1, 14. Then we had 48, 14 went in that 3 times, 6, and then 14, 6 and 2, and then 6 equals, 2 times 3, so we stopped here. And we found out the greatest common divisor was 2, right there. So what we're going to do is take these equations that we found earlier, and we're going to work backwards to help us find the values for x and y that satisfy these this equation. So we're going to say the greatest common divisor 2 is equal to, and you're going to solve for 2, and you get 14 minus 6 times 2 in this first equation here. So 14 minus 6 times 2. And then we also know that we know that 6 is going to be equal to 48 minus 14 times 3. So 6, 48 minus 14 times 3, and that's all times 2. So we're going to clean up here a little bit. So that's equal to 14. And then we have, let's see, plus 48 times negative 2 plus 14 times 6. So the way I did that is I distributed this minus sign to here with a 2. Got the 48 here, so there's my minus 2. Minus sign goes here. These two negatives make positive, so I had 14 and 3, and then I also had a 2 distributed, So that's how I got 6. 3 times 2 is 6. So I have 114 here, but I also have 6 more here, so I'll get 7 with 14. 14 times 7, and then plus 48 times negative 2. And then the last thing to do is to solve for 14 in this first equation up top. So we're just going to subtract the 48 over 48 times 1 from 62 and replace that with the 14. So that's 62 minus 48 times 7 plus 48 times negative 2. Okay. Hey. Okay.
What, did you fix those up?
What's that?
Those flowers?
No.
Oh, it came like that?
Yeah.
Oh, I figured we'd have to fix them. Yeah.
Yep. Excuse me, that was my dad coming inside, so here we go. We're continuing here. And I'm going to distribute that 7 and minus 48 there. So we have 62 times 7 plus 48 times negative 7. And then plus 48 times negative 2 here. And we can combine those together. The negative 7, negative 2, well, that's negative 9. And then we also have 62 times 7. Okay, so there we go. We have 62 times 7 plus 48 times negative 9. So let's check to see if we get 2 from that result. 7 times 2, 14. 42, so that's 434. And then 48 times 9, 72. So that's going to be 36. 7 is 432. So 434 minus 432 gives us 2. And that's what we wanted. All right. So we found our integer solutions. We found that x is equal to 7. Or actually, nope, we reversed these. let me erase this here, because we gotta go x is with the 48 and y is with the 62. So I'm going to delete that. Hang on just a second, guys. Thank you for your patience. And so the x actually goes with the 48 here, so we have x equals negative 9, and then y equals, with 62, that's going to be 7, right? So y equals 7. So we found 2 integer solutions. X is negative 9, y equals 7. But are those solutions unique? And, you know, the answer is no. Actually, you can find many more, infinitely many solutions. And so the way that we're going to find the rest of those solutions, we will review that on the next board. So we'll delete all this here. And again, if I'm going too fast in the video, please just rewind or pause the video, and then you can review or take time to pause it and write stuff down. Okay. So we're going to write down our equation here. We got uh-oh. I accidentally clicked something there. I meant to click undo. There we go. Oh, that's technology for you. So 48x and then plus 62y equals 2. And we found that our two solutions that we got is x equals -9 and y equals 7. So the way we can find these the general solutions is we'll use these two formulas here. We have x equals x1, and then we have minus b over d times t, and t is an integer, some integer, and then y equals y1 plus a over d, t is an integer. So the way to get this general solution for x is just to take the x1 and y1s that you had, we'll call those arrows. Right there, x1 is -9, y1 is 7. And then take your value for b. We found b is 62 with the y, and then a is our 48. That's with the x. And then we know d is equal to 2. Right? And then that'll give us, and then t. And we just leave t alone because that's our independent variable, where you can just plug in any integer in for t. So we'll just make a note here. T is an integer. So when we do that, we're going to get x equals, or x1 is -9, and then we have minus b is 62 over d is 2 times t. So this means that x equals -9 minus 62 divided by 2 is 31, so it's 31t. And then for our y, we have our y1, which is 7, and then we're going to add that to a, that's 48, divided by d is 2 times t. So that's going to give us y equals 7 plus 48 divided by 2 is 24t. And there's our answer for y. So those are the general solutions for x and y, you can find. And the way you can check that is to take this 48, multiply it by x. Take this 62, multiply by that y right there. Add those together and see if you get 2. And we can actually do that here. So let's see, 48, do our arrow on the side, -9 minus 31t. So might want to get your calculator out to crunch these numbers. So 48 times -9 is -432 minus 48 times 31, 1488 t. Okay, and now we do the next thing. We do 62, multiply it by that y. 7 plus 24t. So 62 times 7, that's 434. Plus, then we do 62 times 24t. And that'll be 1488t. Yeah, so if we combine these together, you got negative 432 minus 1488t. And then plus 434 plus 1488t. So you notice that negative 1488t and positive 1488t cancel out, so we don't have any t's left over. And negative 432 plus 434 equals positive 2. So we know that our solution is correct for x and y. These are the answers. Okay, so in that part we actually learned, how to find the GCD using the Euclidean algorithm, how to solve for the Diophantine equation, finding just our x and y's by working backwards, solving the equations, and then once we find those, then we can use this formula right here, these general formulas for x and y, to get the general solutions to the Diophantine equation, which we did here, and that helps us find all possible solutions. So again, my name is Ben. I want to thank you for watching this video on the division algorithm, the Euclidean algorithm, and we also covered modular arithmetic as well. Please stay tuned for more math videos, and you take care and have a good day. Bye-bye.